Hello, today we will discuss Gauss Theorem, which tells us that if we take any positive integer n and discuss all its divisors d and take the sum of phi of d for every d, the phi of d is the Euler's tangent function which counts the number of positive integers which are less than d and coprime to d, so their GCD with d must be 1, then this sum must be equal to n. To prove this, we need to take the set of SI. There we need to insert numbers m. There m is less or equal to n, and GCD of m and n equals di. We will now show that the size of SI must be equal phi of n over di. To show this, we need to define m equals d times m prime. Their GCD of di times m prime. Their GCD of m prime and n equals 1. Now look at all numbers in the SI. They must be di times m1 prime, di times m2 prime, and in total we must have di times m phi of n over di prime numbers. And now show why it's correct. We can see that m prime must be less or equal to n over di because we know that m prime m was less than d, and if we divide both sides by di, we'll get this equation. And we can also see that m is also coprime to n, so this must be also coprime to n over di, and we can take every positive integer which is coprime to n over di. So in total we must have phi of n over di numbers, and if we take di out of brackets, this set must be something like this: m1 prime, m2 prime, and m phi over n over di numbers. So we have proved that size of SI must be equal phi of n over di, and now we will show that every number from 1 to n must be exactly in one of these sets: S1, S2, S of k. There in total we have d1, d2 up to dk divisors of n. Because we know that GCD of n and this number, any number t, must be only one number, we will see that each number will go to only one set of SI. So we have shown that size of the sum of the sizes of sets of SIs must be equal n. Sum of the SIs equals from 1 to k. This equals n. And now we will use the fact that if di is the divisor of n over di must be also divisor of n. Clearly this is correct because their product equals n. To take the product of these numbers, di and n over di, this equals n. So if di divides n over di must also divide it. So now we will show that this sum equals sum of the numbers from I equals 1 to k, phi of n over di, because we have shown that size of SI equals phi n over di, and clearly this number equals I from 1 to k, phi of di, because every divisor must be given in both of these forms, n over di and di. So we have shown that sum of the f of di's must be equal n. So this was all we wanted to show today. For the next video, we will use this very useful fact to prove that there exist primitive roots for every prime number.